Hello, Lucia. Hello, Smart Coder. Welcome to the stream. Today we're gonna do something new. We're gonna be solving the CodeForces Deep 4 contest. Welcome to Twitch. All right, so let's do it. Let's get started. So this is the contest. Okay, I'm leaving got out solve. Okay, I'm gonna upload this to YouTube afterwards, so maybe you can watch it later. Okay, so let's start with the first problem. Well appreciated. All right. So this is problem A, stair, peak, or neither. You're given 3 digits, A, B, C. Determine whether they form a stair, a peak, or neither. And here we even get the formal condition. So we can even translate this into Python code pretty directly. So there's not much to do. This is the first problem. Not much to say here. We just test the conditions. So we want to read the number of test cases, and then that number of times we're going to be reading A, B, and C. This is how we read input in Python. And so if we have a stair, which is this, we print stair. If we have a peak, which is the B is greater than A and it's greater than C, we print peak, and otherwise we print none. Let me check if I got this right. Yes, it's none. Stair, peak, none, and the condition is exactly what we did. So let's run it. Why not? With the standard input, with the examples, and run code. I've never used this. This is the first time I'm using this playground. It's pretty cool. Okay, so we get stair, none, peak. So maybe we can just copy this and check if it matches, and it does. Cool. So let's paste this. We're using Python. PyPy is usually faster. And it's problem A. So, okay, we got it right. That's cool. So let's move on to problem B. Cool, I never seen the playground. Yes, yeah, that's pretty interesting that they provide this feature. It's useful for this, so I'd rather do the whole stream in the browser, so that's why I'm using it. All right, so upscaling. You're given an integer n, output an 2n times 2n checkboard made of 2 times 2 squares, alternating the dash, the hash, and the dot, with the top left cell being. Okay, so this is a well-known problem. So here, notice that we care about the parity of the sum of the rows. So example, so if we have, okay, this is 2 This has AI now? What? What's that? No, here I want this stroke width. Okay, so notice how it changes. So if we are here in this cell, so this is R and this is C. So if we move one to the left, then the sum R plus C is going to change. You're going to add 1, right? Because the column is going to increase. So now the parity changed, right? So what I'm saying is that we want to look at the parity. So the sum mod 2, that's going to determine whether we are on a black or a white cell. And this is the explanation. If we move here, we increment the column 1, so that's going to change the parity. If we move here, but then if we move here and the distance is 2, then the parity is changes again, so it's the same as the original. So that's why it's the same color. But here, the only catch in this problem is that we want to stretch the board. So we're asked for a board of 2n by 2n. So we can do that just by dividing the coordinates by 2. So let's see, we still want that. And here the only input, I think it's n. And so we want to go over the rows on a board of this size, 2n by 2n. That's what we're told. And this is going to be a hash if so R divided by 2 plus C divided by 2 mod 2 is 0. Hey, I'm hungry. Thanks for the follow. So in this case, we want the let's add this to a list. So here the list want to append this character in this, right? Because hey, Glamp1, thanks for the follow. Still gotta virtual this. Okay, so maybe you can watch it later if you want. All right, so because I'm gonna spoil it otherwise. So and then in the other case we do this, and that's what we append. And here we want to print the whole row. So for that we can do well, I guess we can join it. We can just join it. And I think this is it. Let's try it out. GL bro, thank you. So we can out. Let's run it. And it looks okay. So let's do the same method of searching. And it matches. Cool. So let's submit. All right, upscaling. Accepted. Cool. Cool. So let's move on to question 3. Good idea to do division by 2. Yeah, that's a little trick to do this. that stretches. So it might be counterintuitive that dividing by 2 stretches, but if you think about it, you'll get the intuition. Because all those, for example, here, all these elements will be considered, these 2 are considered 0, then these 2 are considered 1, then these 2 are considered 2, and so on. So that's why it's like you're changing the resolution of the image, in a sense. You're losing information of the coordinates. So yes, you're like pixelating, kind of. Anyways, so problem C. I see. So given the time in a 24-hour format, output the equivalent time in a 12-hour format. Okay, I guess we already know this. So we can, so usually, hey Jake, thanks for the follow. Thank you. So I guess we can just, so what is the input here? It's just the time. So let's do the following. So usually I like to use a function here. So let's print and then let's use a function to parse it, to parse the date. So we want the hour is going to be the first 2 digits. We want it in minutes, and then, well, do we need to? Well, no, I guess not. I guess we just want this. So, and here, this is the number of, no, here, because there's the colon. All right. So now we have the hour and the minutes. And so just a couple of comments to make this in a principled way. So let me clear this. So here, so notice that the minutes are not going to change. So here we need to change to adjust the hours. So let's say, so if we have one, oh, why is this always choosing the stroke? Okay, so if we have one, it's going to map to 1. Okay, then this is the hour in the 24-hour format. So 2 is going to map to 2, and so on. 12 also maps to 12. But then 13, here we wrap around, right? Here we wrap around and we go to 1, and so on up to 23, which is 11. And then here we have 0, which maps again to 12. So notice that we are actually wrapping around, but the detail here is that this is 1 based. So one way to do this is to translate to 0 base, do the mod 12. So there are 12 elements that get repeated, and then add 1. Okay, so Well, first of all, we have the suffix, so the suffix is going to be PM if H is greater than or equal to 12, else is AM. Okay, but then H is going to be, so I subtract 1 to make it 0 base, then I do the mod 12, and then I add 1. What is here? So the special case is where we have 0, right? So when we have 0, after we subtract 1, we're going to get -1. And when we do mod 12, that's going to give us 11. And then when we add 1 again, we get to 12, which is what we want. So this is going to work. And so here to do the padding, we can use this Python formatting string. We can do, so we want the hours, 0.2 decimal, and then here we want the minutes, also 0.2, so we want to pad with zeros, and we want 2 places. And then we want the suffix. Okay, so I think this should work. Let me try it out. And again, same idea. Kind of looks okay, and it matches. So let's submit. So I guess you could do this without the, so you could just have an if statement for the 0 case, but I think this is more elegant. All right. All right. So, okay, so let's continue with problem D. Did you like that trick, Lucia? So far, so good. All right, so product of binary decimals. Let's call a number binary decimal if it is a positive integer and all digits, I like it, yes. And all digits in its decimal notation are either 0 or 1. For example, this is, okay, it's clear what it is. Given a number n, you're asked whether or not it is possible to represent n as a product of some, not necessarily distinct, binary decimals. Okay. And n can be 10 to the 5, 100,000. And then we have up to 50,000 test cases. Okay, and we just say yes or no, that's all. So here we have a few examples. So we have to factorize this number, the given number n, into numbers that are binary decimal. Okay. So the numbers are relatively small. So it's not 10 to the 9, it's 10 to the 5. So that's important because your intuition here should be that you can't have too many factors, right? If you have, so for example, 11, if you have 5 11s, so 11 to the 5th power, then you already go over 10 to the 5. So seems like, and 11 is the smallest. Well, you also have 10. but let's see if we can make some observations. Let's clear this and choose this. Okay, so we can have a function that tells us. So first we can check if it's deck if it's bin deck of n, and if it is already bin deck, then we return yes. Okay. So now let's assume that n is not already bin deck. Then notice that you never have to use you never need to use powers of 10 as factors, because yeah, I mean, if you have a power of 10, you can multiply it by, so if you have, for example, 11 and maybe 101, and then you have 100, but you can make this two together, right? And this is still going to be a bin deck number if you multiply by a power of 10. So now you could make this like this without changing the product. And so that proves that we never need a power of 10 as a factor. And of course, we never need the 1, so 1 is not a factor here. So that means that, for example, so maybe we can check the cases where we have 5 factors. So if we have 5 factors, we consider the minimum number, which we just proved, the minimum factor we just proved is 11 because 10 doesn't count. So this, we know that it's already greater than the maximum. Okay, so that means that we can have 5 factors here. After, of course, after we have eliminated, this is all based in this fact, the fact that the number is already not binary decimal. We already eliminated that case. So let's think about the case of 4 factors. So for 4 factors, notice that if we use a number, so I'm gonna claim that we can only use the smallest factor, because if you even use one of the, so 101 is the second smallest, right? There are no numbers of 2 digits that are bin deck and are greater than 11. So the next one is 111. So even if you use one of this and then you use the smallest one for so notice that this already is greater than, so this number is already greater than 10 to the 5. So that means that if we have 4 factors, so this number is already also greater than 10 to the 5. So that means that if we have 4 factors, the only case is this. Okay? That's the only possibility. So we can eliminate that also with an if statement at the beginning. So now we're down to 2 or 3 factors. So we can just try them, right? So we know that the smallest factor cannot be greater than the square root of the number, right? For example, in the case of two factors, if we have so the square root, why don't I get this? Okay, maybe Wolfram Alpha. So this is going to be 10 to the 2.5. Okay, so it's 300. It's around 300. So that means, so we know that the smallest factor. So what are the candidates of the smallest factor? Well, we know it's 11, and that's the only one with 2 digits. And then if we have 3 digits, notice that, so we exclude the power of 10, so 100, we don't count it. So we have 101, 110, and 111. So these are the only candidates for being the smallest divisor of our number. So maybe we can start coding. So then we can handle these two cases, the 2-factor and the 3-factor, by brute force, because there are only very few. So here there are only 4 candidates. So we can just go over all the possibilities here. So okay, so this has only a number as an input. So we know. So what have we? So let's write down the binDec function. So we want to go over the digits, well, the decimal digits, and if the is not in this range, we return false. All right. So this tells us if a number is binDec. So if n is already binDec, then we return true. Oh, here, let's do this. Let's say yes if good, else no. So I like to handle the input output. Return true. Oh, yeah, you're right. Okay, so now we handle the case of 4 factors, which we said the only option was 11. And then we're going to have the candidates that we enumerated. So it was 11, 101, 110, and 111. And then we're going to try so this is the smallest factor, which has to be one of the candidates. And if it's already greater than the square root of n, then we haven't found any. And we want to see if n is divisible by x and n divided by x, so the other factor is bin dec, then we found a case of two factors. Okay, and now, so in the end, if we don't find any, we're gonna return false. So here we're gonna deal with three factors. So for three factors, so first the smallest factor. So we know that if this factor cubed is already greater than n, then we haven't found it. Okay, so now here we check if n is divisible by the candidate, and now we have this reminder. So this is the other factor that we also have to break down into two. So, and we know that it cannot be less than cand of I. So we go from of j from I to this, and so now if cand of I times cand of j squared is greater than, so I'm doing this tight, but it doesn't matter because the numbers are so small. So in that case, we are already over, and now we check if well, I guess we don't need this, so we already have n2, so we can do this. And now we want to check if n2 is divisible by this candidate, and if n2 divided by this candidate, so if it is a bin dec, so in that case we found a solution. So this should be it. Let's run it. Good is not defined. I should have renamed this. Cool. This one threw me for a loop because I thought n times factors wouldn't pass. So the n times the prime factors. So the prime factors, you know that there are a few of them. There are, oh, this is a different problem. Okay. Okay, so I think this makes sense. Let's do what we've been doing, and it matches. So let's submit. Wrong answer. Whoa. Let me think. So bin dec. This makes sense. The candidates, I think they're right. And here, this makes sense. Break. Yes, if the cube of the smallest factor is greater than n, then I'm already over. So then I check if it is a divisor, and I get n2, and then j must be at least I. And if j is already greater than I break, oh yeah, this is 0. Oh my god. Why did it work? Well, I guess maybe we don't have any example here. Okay, let's try again. Sorry about that. Accepted. Lol, didn't see that. Yeah, that was like a typo. Good catch. All right, accepted. Cool. So let's go to E. Nearly shortest repeating substring. So we're given a string S of length n consisting of lowercase Latin characters. Find the length of the shortest k such that several, possibly one, copies of k can be concatenated together to form a string with the same length as S. At most one different character. Okay, this is the formal explanation. Okay, so this one I think it's even easier than the previous one. So we know that the length of k must be a divisor. So if we repeated k x times, we get the length of c, right? So we know that k, the length of k must be a divisor of the length of c. So that already gives us a search space that is pretty small because the number, so n goes up to 200,000. So the number of the divisors of a number is of order of the square root. So that means that it's around 300. So we can try all of the divisors, right? And then notice that, so there's a special case, right? The case where k is equal to, so there's only one. So in that case, we can always do it, of course. But if there are more than one copies of k, so if x is more than 1, then we can consider the first two occurrences of k, and notice that they can both be different than the corresponding string. If they were both different, then you would have more than one different characters. So one of them must be the same as C. So we can try both of them. We know that one must be true. So if we found it, if it satisfies the condition, then we found it. And if it doesn't, then we know there's no solution for that divisor. So we can implement this pretty easily. I'm gonna have to watch bot later. Sure, yes, I'm gonna even upload it to YouTube, so you can watch it there. So here we get an n and we get a string, okay? And we have to return the smallest. So here we have to return a number. So like I said, we're gonna need the divisors of a number. So let's write a function for that. So this is pretty standard code. So we try all. So and we wanna go in order. So from smallest to large. So that if we find one that works, we just can return. So for that we're gonna have two lists. So this is how I do it. We're gonna have two lists, the head and the tail, and so we have to go up to the square root of the number, and if it divided, then we add this to the head, the, because the first is going to be 1, which is going to be a divisor. So it goes from the smallest to largest, but then the other divisor is n divided by d, but that is going to go from the biggest. Initially it's going to be, in the first iteration, it's going to be n, and then it's going to go down. So that's why this is tail. That's why we add them to lists. So head is going to be in increasing order and tail is going to be decreasing. Okay, and here we have to take care of the square root, because if we do it here, we would duplicate a divisor. So here we just append the, and here we return head and tail, but tail reversed. Okay, so that's going to give us the divisors in order. Okay, so now we go over the divisors of n, and we want to check if we want to check if d is different than n. Because if we get to n, we at the end we just return n, okay? But here we are going to we're going to get x and y, which are, so I said that we want to try with the first two substrings, okay? So here we get the first d characters, and here we get the second d characters, and if it's good, if x is good or y is good, then we return d, because we know this is the smallest one that works. So here we gotta do this. So oh, sorry, so this is not, so I want to know if this is so it's x multiply this many times, so that, and here it's y multiply the same number of times, they are both the same length. And so here good means that they have at most one difference. Nice idea to look at the first two strings, two substrings, yeah. So here we just want to sum the differences. So for x, y in this, if x is different than y, we want to add 1, and we want this to be less than or equal. Okay, so this should do it. Let's get the Let's run it. And we get this. Let's match it. And it matches. Accepted. Cool. We're getting there. We're getting there. Okay, so this one, 0, 1, 2, 3. Find the minimum height of a root tree with A plus B plus C vertices that satisfy the following conditions. A vertices have exactly 2 children, B vertices have exactly 1 child, and C vertices have exactly 0 children. If no such tree exists, you should report it. Okay, so, and these are less than 10 to the 5. There's at least one node. Okay. So I didn't notice this limit. So my solution does not. I wonder if there's a less efficient solution that uses this. Anyway, so let's get to the drawing board because this one is going to need some explanations for sure. Hey, unemployed QA, thanks for the follow. All right, so let's see, what can we do here? So first of all, can you paste the link? The problem link? Yeah, sure, sorry. So, okay, so there is a relationship between the number of nodes with 2 children and the number of nodes with in binary trees and the number of nodes with the number of leaves, the number of nodes with 0 children. So for example here you have this, maybe this. So notice that there's 1, 2, and 3 leaves, and there's yes, and there's 1 and 2 nodes with 2 children. This one is a special. Okay, so here the number. So let's code this. So let's color code this. So red are the nodes with 2 children, and green are the nodes with 1 children, and blue are the nodes with 0 children. Okay, so here it seems that, well, in this case, the number of nodes it's 2, and the number of nodes of blue are 3. So, and this is going to always, so if you always have one leaf more. So for example, if you have the tree of only 1 node, there's 1 leaf, and there are 0 nodes with 2 children. Okay, so what I'm saying is that the number of reds plus 1 is always the same as the number of blues. This is a well-known. And how can you think about this? I didn't follow that. No, I did not prove it yet. I'm just claiming. So I gave an example, and I'm saying that this is always true, and I'm gonna explain how to think about it. So, and I also said here, in the case of only one node, it is true, right? Because you have 0 nodes with 2 children, so 0 reds, and 1 node with 0 children. So 0 of this plus 1 equals 0. So it's correct in the base case. Okay, do you follow? So now let's say that you have a tree. So we're thinking inductively. So let's say that you have a tree and you want to grow it. You want to add 1 node to it, right? So since this is a binary tree, you can add a node to a leaf, right? A node that has no children. So you add this node. Or the other case is to get a node that already has 1 children, and we add 1 here. Okay, so notice that think about the changes in the number of nodes of each kind of each of the 3 kinds. Okay, so here notice that this node had 0, and now it has 1. So the number of nodes, so I think it's kind of annoying to use the colors every time. Maybe I can call them something else. Okay, so let's say n1 gets incremented by 1, because when we add this node, now we have 1 more node that's only 1 children. That's n1. But n0 doesn't change, right? Because this was a leaf. It's not a leaf anymore, but now we added this leaf, so the number of leaves stayed the same, and the number of nodes with 2 children also did not change in this case. And what happens in this case? So in this case, we added 1. So the number of nodes with 1 node don't change, okay? But the number of nodes with 0 was incremented by 1, okay? So we incremented this by 1, but the number of nodes with 2 children was also incremented by 1. And these are the only ways to grow a binary tree. So notice this is interesting. So here, notice that every time we make a change, every time we add a node, these 2 change together. They either stay the same, or they either or we add 1 to each. So that means that they will always be the same. So at the beginning, this equation stands, and then if we add 1 to each, or if we add 0 to each, the equation is going to it's going to be invariant. Okay, so that's how you prove this. So and that already gives us code, because if So in the problem, these are called A, V, and C, right? So this N0 and 1 and R2. So we know that if A plus 1 is different than C, we return -1. We cannot do it. Okay. And notice that if you don't have that, you can think about it in the same way. So notice that here, whenever you have a tree, we can add one. We can find a leaf, and we add. There's always there's always a leaf, and we can add one node to the leaf. How to handle the pressure in Scrum sprints? That's a little off topic right now, but we can talk about that later. I think I am experienced. Anyways, so here we we could add, we could always add one node to a leaf, and then we add another node to the leaf, and so yeah, I think this wasn't 0. This was -1 because this one has one child, but now it has 2, so it was subtracted. So this was -1, but it doesn't matter for the proof. We only needed this to be the same, this 2 to be the same, and this 2 to be the same. Okay, so notice that if we do that, we add 1, then we add the other. We're incrementing the number of n2 and n0 by 1. So that means that we can do that until we get to A and C, and then we can always keep doing this this change of adding a node to a leaf. We can do that as many times as we need to get to B. So that means that we can always, this is the only condition where we cannot do it. Otherwise, we can always do it. So now we have to focus on the minimum height, which is what they want us to optimize. So let's keep going. So let's say that we have a tree. Oh, again, this stroke. So here, here. Let me see. I'm trying to do a diagram that explains. So we're gonna. So notice that if we pack the nodes, so we want to make a complete. If we make a complete binary tree, that's going to pack as many nodes as we have, and that's going to minimize the height. So remember that a complete binary tree is a tree that is full, that it has all the levels are full except the last one, and all the nodes at the last level are to the left. So let's add all the red nodes, so the nodes with 2 children. Let's add them here. Okay, let's add them. So we're gonna add them in order. So this is node 1, this is node 2, this is node 3, this is node 4. So we add all the red nodes at the beginning. Okay, so now, so we know that this is a red node, so it has to have 2 children. And this has 2 children, and this has to have 2 children. Okay, that, and notice that this satisfies our equation, right? Because there are 4 of this and there are 5 leaves. Okay, but we already checked that. So now let's find. So what do we want to do? We want to see if this height. So here we have height 3. We want to see if this height is enough. Okay, so for that to be enough, so notice that now we don't have any more nodes of 2 children. So we have to use these ones to add the nodes with. We want to make these nodes green, for example. Okay, so that means that they will have 1 child, and for this height to be sufficient, we need the number of nodes of 1 child to be less than or equal to the nodes that are here. Okay, so we need to count those nodes. How do we do that? Okay, so let's find out this height. This height h here, it's 2, right? And remember that the number of nodes of a full perfect binary tree of height h is this, right? So for example, here h is 2, so 2 in this case we would get this, which is 7, which is how many nodes we have here, right? So this is 5, this is 6, and this is 7. Okay, so now we have this height, and so which means we're pointing. We have the label of this node, right? So if we subtract, and this is the label of A. A were the number of red nodes. Okay, so if we subtract those 2, we're gonna get how many we have here, right? So that means that this number was the smallest h such that 2 to the h plus 1 minus 1, which is this node, is greater than or equal to A. Okay, so we found that. So now we calculate how many green nodes there are, which is this node, the 7 in the example, minus, hey Path, thanks for the raid. So this is this node minus this node A. And like we said, hey NCC, welcome. So like we said, we want the green nodes to be greater than or equal to B. In that case, we don't need any. It's sufficient with this height, right? Which this height we know that is h plus 1, which in this case is 3. Okay, so if we can put the nodes in this way, in this configuration, we know that that this is enough. Okay, so we can do this if, and in this case we just return h plus 1. Otherwise, we are going to subtract from h. So we're gonna set these nodes. We're gonna set them anyways. Okay, so we're gonna fill this. So we're gonna make all these nodes green, and so we want to subtract from B these nodes that we already placed there. Okay, so now we have something regular here, which is easier to think about. So we know here the number of nodes here is it's C, is the number of leaves. And now notice that to minimize the height, we want to add, so we want to make green first this node, then this node, then this node, and so on. We don't want to expand here before we used all of those nodes, of course. So we want to make this green, then we make this green, so on. And so notice that this is going to be the division, the seal division of B after we removed already these 3 nodes. The division seal is going to tell us how many more nodes than H plus 1 we need. Okay, so, and that's going to complete our solution. So let's code it. So that wasn't that was a long one, I guess, but I wanted to explain it to explain it all, even the property of the binary tree. So how do you think about binary trees inductively? So here again, so let's read the input, which is only three values here, A, B, and C. Okay, so we have a case where we cannot do it. So if A plus 1 is different than C, then we cannot do it. Now we wanted to find the smallest, so this is what it's written here, the smallest h such that, so while this is not true, we want to increase h, okay? So while, so this is how you do powers of 2 with shifts. So this is 2 to the h, but we want 2 to the h plus 1 minus 1. Those are the number of nodes in the perfect binary tree. And if this is less than, let me check that. Yes, if this is less than A, we want to increment. So now we found the smallest h. So now we want to check if 2 to the h plus 1 minus 1 minus A. So these are the number of green nodes in our diagram. So if these are greater than or equal, then we return h plus 1. Otherwise, we subtract from, this from B, and now we just divide. So we want the B divided by C, the number of leaves, but the seal division. So we add C minus 1 to make it a seal division. And that should be it. I mean, it's the explanation is long, but the code is pretty short. Oh, yep. So, Okay, so we got some results and they don't match. They don't match. Okay, so let's think about it. I think this is correct. And is this what we wrote here? So here we wanted to find this height h equal to, so we wanted 2 to the h to be greater than or equal to a. So if this is less than a, we keep incrementing it. This is less than a, we keep incrementing it. And here, so we subtract that from, so now we know that this is greater than or equal to a. So we check if this is greater than or equal to b. And in that case, we want h plus 1 to be the result. Because and then here we subtract that from b and we just divide. Yeah, I think the problem, so let me see which examples are failing. So 201, so the second one, oh, but a bunch of them are failing. So here, maybe I can use the child of A. And now I did this. I mean, this should be the same thing. Oh, I know what's wrong. No, wait. Yeah. I know what's wrong here. So here, I forgot. So this is how many we add to. So this division gives us how many we have to add in addition to the h, to the height h plus 1. So I think this should be it. Oh, yes. So, well, I think now, so hello, David. So I think now we got them all right, except the second one, which I think it's an edge case. Because if we have, if we have 0, so I think this is the case where we have 0, the second case. We have 0 as A. So that means that we have 0 nodes with 2 children, and that means that we had only 1 leaf, and so the height is going to be B in this case. It's going to be the number of nodes with one child. Why in Python? I like Python. I do sometimes C++ as well. Okay, so let's try this special case. I think now we got them right. Yep. So let's see if we get accepted. Accepted. Cool. So the last one. Let's get to the last one. Here's the link. For understand Python is fair, for competition do C++. Yes, I'm focusing on teaching, not on competing. But I think what matters is how you think and how familiar. So you have to learn some tricks. Hey, thanks for the follow. You have to learn some tricks to make Python work. But once you do that, I think you can go very far with Python in CP. Anyways, so let's do the last one. So, nice one. Vladislav has a playlist consisting of n songs numbered from 1 to n. Song I has genre G of I and writer dub of Y. He wants to make a playlist such a way that every pair of adjacent songs either have the same writer or are from the same genre or both. He calls such a playlist exciting. Okay, this thing about the strings that they're long, it's just a red herring, I think. Might not always be possible to make an exciting playlist using all the songs, so the shuffling process occurs in 2 steps. First, some amount, 0, of the songs are removed, and then the remaining songs in the playlist are rearranged to make exciting. So he doesn't like when songs get removed, so he wants to make as few removals as possible. Help him find the minimum number of removals that need to be performed in order to be able to rearrange the rest of the songs to make the playlist exciting. Okay, so here the giveaway, the huge giveaway is that n is up to 16. So that should be so you should pay attention to those kind of small numbers. Okay, and even here they tell you that the sum of 2 to the 16, 2 to the n does not exceed 2 to the 16. So it seems that we can do something with subsets. This is what this is suggesting. So this is the number of subsets. So you're trying to remove songs. So that means that you have to deal with subsets of the given songs. So notice that we can think about this as a graph, because we have songs that can be adjacent, that can be that can be adjacent when they have this condition, okay? And then you can think about a playlist as a path in a graph. So you're at one song, at one node, and you know which songs are compatible with it. And so you move on to another song that is compatible, and then you move to another song, and so on. And you want to make a path that visits every node once. And that is called, in graph theory, that's called a Hamiltonian path. And it's a very well-known problem. There's a DP solution using bit masks, which is what we are going to implement here. So we're going to do this. So given that Python is not good at deep recursion, well, it's not good at recursion. It's a little slower. And on CodeForces, the time limits are tight. We're going to do bottom-up DP. So that's one of the tricks that you need to know when using Python. In CP, you usually need to go for bottom-up DP. All right, so I'm going to be explaining what I code. So I guess we get n here, and then for each song we get this. So how do we want to do this? Yeah, so we're gonna save here the so here we get the genre and the author, I think. Sup coach, hey Midnight Simon, welcome. We're doing the CodeForces contest. Okay, so we get G and W. The writer and the genre of the song. All right. So these are strings that might be long. So let's have some IDs for them. So G A IDX and some W IDX. So if G is not in the index, we give it an index. And if W is not in the it doesn't have an index yet, we give it. So this is just to deal with the long strings. I don't want to have any, I don't want to work with long strings. I'm not sure if it's necessary. Anyway, so now we want to have, so let's add the G's append. Yeah, let's make it. So here we have the songs. So let's add the songs. It's going to be represented by the G index and the W index. So that is my song. So I want to create an adjacency list so that I don't have to deal anymore with any of this. So here's my adjacency list, and I just want to go over all the pairs, and if the songs, so if they have the same genre, or they have the same writer, then they should be adjacent. Okay, so now we just solve this. We forget about this nonsense of songs and all of that. We forget about the story. Okay. Lol. Yes. So now we just think about Hamiltonian path that grabs and all of the nice stuff. We don't have time for all this bullshit. So I usually don't like calling this DP. So let's say that, let's call it good. So good means that we have a Hamiltonian path, so we can do the, yeah, let's go back to the songs if you want. So you can play the songs so that they satisfy all the songs in the current subset. So we're gonna have two things in our state. We're gonna have the node, the song that we're at, and the subset of the songs that we still have to play. Okay, so let's say this is true, and these are the number of subsets, right? This is 2 to the n. These are the number of subsets of songs, and these are the number of songs that I can be at. So we're gonna find, oh, here, this is the problem with this. Oh, this is the problem with this editor, I think, that I have to import things. But I don't get the warning. All right. I don't get warning. That's a problem. Anyway, so okay, so first we have the subset. Let's call it SS, the subset, which is going to go, those are all the subsets of the songs. And then I is going to, let's call it U, I like U for nodes. So this is the node that I'm at. And notice that I consider the current node, the node that I am at, as already visited. So it shouldn't be, if it's already, if it's on in the subset, then I just skip. This is not a valid state for me. Okay, so now, so let's initialize this. So this is U and subset, and if the subset is empty, then it's good. Well, I guess I could do just this. Yeah, I usually. So if the subset is empty, I mark this as already, I already visited all the nodes. So it's trivially good. And so now I go to all the adjacents of U, and if I haven't, so if it's in the subset of the nodes that I have to visit, then I try visiting. So I want this to B. So now we move to B, and we turn off. So we remove from the set B. Okay, maybe we have just visited it. And so now if this is good, if this is good, then we need to count how many songs we removed, because that's what we want to minimize. So let's count out that here, and then we're going to minimize it, and we're going to return rest. So how do we count how many songs we have removed? So I think so from all the songs that we have to play, that we played, are the subset songs and the song that I'm currently at. But this should be bit count. But I think this doesn't work in CodeForces, the bit count, because it's a new method. But yeah, let's try this and see if it works. Oh, so I didn't. Yes, I assumed these were ints, which they are not. 0, 0, 4, and 3. So that's correct. Well, let's try and see. So what is the version? So with 3.9. So let me find that. So beat count int. Yeah, Python 3.10 or later introduced the beat count. So that means that it's not available here, which is 3.9. Okay, so I'm gonna make my own. So I already explained how to do this in a clever way. So which is this. I'm not going to explain it now. And so here we want to do this. So it should return the same thing. That's right. And let's see if we get it accepted. Nice. That was easy. So yeah, this is a very famous problem. Cool. The code, as you see, is not hard. You gotta think through it a little bit. So okay, so that's the full contest. We've done them all in Python, even though people were not believing in Python here. But we got it to work. So that's all I have for now. I think this one was pretty interesting. I hope you learned a few ways to think about trees, induction. That's pretty useful for algorithms. So yes, thanks. Yeah, thank you for watching, and I see you in the next one. Bye bye.